Welcome to day 3 of remote learning. Today's lesson is the joy of establishing trig identities, which reminds me, if you're starting to go a little stir crazy, you need something to watch on Netflix. The Joy of Painting with Bob Ross has been added, which also might help you chill out a little if you've been checking the stats on Worldometer or starting to panic. So today, I'll take you through 4 examples in establishing trig identities and talk about the algebraic skills that you need in order to do that. In order to find the right steps, I've got a secret envelope here full of bright ideas. I'll put a list of bright ideas on Blackboard so you can consult that as you're establishing your own trig identities, the ones in worksheet 1 and some of the others going forward. I'll also put a list of known identities up so you can consult that if there's certain things you're starting to forget. All right, so here's our first example. Example 1, we want to establish that cosecant of theta divided by secant of theta is equal to cotangent of theta. All right, so let's see. In our list of bright ideas here, what we have, our very first piece of advice is that we always work vertically. Working vertically, that means I've got my canvas not in landscape mode like we had in some of the other videos, but set up here in portrait mode. So for you, that means just working step by step like this down your paper. All right, and then getting started a lot of times in a trig identity is hard. What's like the very first thing you should do? It's going to change from problem to problem. And this one, my first little tip that I got here is maybe I could try a switch to sines and cosines. So I'll give that a try. If I switch to sines and cosines, this will read, instead of cosecant theta over secant theta, it will read 1 over sine theta divided by 1 over cosine theta, just like that. Switch the left-hand side to sines and cosines. And then, we have a fraction division here. So in order to divide fractions, we multiply by the reciprocal. So this expression here would be rewritten as 1 over sine theta multiplied by cosine theta over 1. Of course, that is equal to cosine over sine. And, of course, that is equal to cotangent. And that is exactly what we wanted to prove, that cosecant divided by secant was equal to cotangent, and that wasn't so hard to do. Example 1 is in the books. All right, let's take these off of here. Try to leave the tape. Work. All right, in our second example, we want to show that the product of 1 minus sine squared and 1 plus tan squared, that big messy product there, is equal to nothing other than 1. So 1 minus sine squared times 1 plus tan squared is equal to 1. Okay, another piece of advice here, something that I should have mentioned last time, is we're going to start on the more complicated side. So the more complicated side is clearly the side 1 minus sine squared, 1 plus tan squared. So I'll take that and I'll rewrite it right here, nice and big, so it's not all smushed up. 1 plus tan squared. Okay, so that's a good time to point out that when you're establishing a trig identity, it's very different than solving an equation. You're not trying to identify a value of theta that works. In fact, we want to show that every single value of theta works. So the equal sign has not been established. So what I do is I have a series of vertical steps that establish that equality is true. I show that this product here is equal to something else with a little bit of algebra, and on and on and on until I get 1. So, okay, well, what now? I think a lot of us probably would be tempted to foil, to start multiplying 1 by 1, and 1 by tan squared, and sine squared by 1, and so on and so forth. And that would be a good step to try. When you try it, you'll notice that the expression starts to complicate more, and you just, how am I going to simplify it into 1? So sometimes you'll do that. Sometimes you'll write out a series of steps on your proverbial canvas, and then you'll decide, well, wait, you know what, I got to take a few steps back and erase and start to undo that. In some problems, multiplying out would be a perfect thing to do, and it'd be very productive, and it'd get you toward your goal of showing what the left-hand side was equal to. But there are other strategies too, and I'll show you one here. Use a known identity. 1 minus sine squared that I see right there in parentheses, that is that's something you want to start to recognize. 1 minus sine squared, we remember back to when we started the unit circle, and we say, oh, sine squared plus cosine squared is equal to 1. And as a consequence of that, that means 1 minus sine squared is equal to cosine squared. So I'll sub out 1 minus sine squared, and I'll sub in cosine squared using that known identity that sine squared plus cosine squared is always equal to 1 for all values of theta. Great. And now you might think, hey, I'm going to distribute the cosine. All right, if you did that, you'd probably solve it in a couple steps or so. But I want to point out that there's another known identity in this problem, and that's 1 plus tan squared. 1 plus tan squared. As a consequence of sine squared plus cosine squared equals 1, we were able to derive 2 other Pythagorean identities, one with secant and tangent and another with cosecant and cotangent. This is the secant and tangent variety. So I'll sub out 1 plus tan squared for what is always equal to for all values of theta, and that is secant squared. So I'll have cosine squared multiplied by secant squared. Oh, and now you keep an eye on where you're headed. You want to show that this is equal to 1. Thought pops into your head suddenly that cosine and secant are reciprocals. That means this is the same as cosine squared times 1 over cosine squared, and that is clearly equal to 1. So I'll just add my equal signs back in here to show that that equality now has been established, that the left-hand side is equal to this, that, the other, oh yeah, it's equal to the right-hand side. So put a happy little check mark right down there, and we are all done.